Okay, I want to pick up with a few more of these mutation problems here, okay? And I just want to go over a few more things before we're done here. And the next question basically says the loss of the binding site for fructose 2,6-bisphosphate on PFK1. So what result is that going to have on phosphofructokinase 1? And the answer to that question is really simple because we know fructose 2,6-bisphosphate is an activator of phosphofructokinase 1. Now, if that's true, if that's an activator and we lose the binding site, we're no longer going to be able to upregulate PFK1 with fructose 2,6-bisphosphate, which was an extremely important activator, if you recall correctly, from the previous videos. F26BP actually could overcome some of the inhibitory properties of things like ATP. So it was extremely relevant and extremely useful, okay? So that's all I'm going to say here, really. I'm just going to say F26BP activates. So it activates PFK1, so PFK1, and the mutation will therefore slow down the rate of glycolysis, okay? So the mutation will slow the rate of glycolysis, okay? And that's basically all you'd have to say for that one. Now, the next one is a little bit more complex, okay? That one says increased affinity of acetyl-CoA in the allosteric binding site of pyruvate carboxylase. Well, first we have to know where pyruvate carboxylase was, and pyruvate carboxylase was a gluconeogenesis enzyme, okay? And it was the first enzyme actually in the gluconeogenesis pathway, okay? And we have to understand what's going on here. We have acetyl-CoA, which means there's plenty of energy. So acetyl-CoA activates the enzyme, okay? So it's going to activate pyruvate carboxylase, since it suggests that there's plenty of energy available, or plenty of material available to make energy, okay? And that's exactly how I'm going to start this. So I'm going to say that acetyl-CoA activates, okay, acetyl-CoA activates the enzyme pyruvate carboxylase. Okay, so acetyl-CoA activates the enzyme pyruvate carboxylase, and I'll say because it suggests that plenty of material is available for energy production. Okay, so quite simply, the first thing I'm saying here is that acetyl-CoA activates the enzyme pyruvate carboxylase because it suggests that plenty of material is available for energy production. Okay, so that's the first part. Now, an increased affinity for acetyl-CoA means that the enzyme will be upregulated before it should. Okay, and that's the important part here. So, because if we're actually answering the question, that's what's going on here. It's saying increased affinity for acetyl-CoA means the enzyme will be upregulated before it should be. So before it should be. Alright, so that's an important point right there. It will be upregulated before it should be, and it will start sooner than is ideal, raising the possibility that there could be a futile cycle, okay, and decreased energy production. So I'm not going to write that, I'm just going to use this last part to explain it. And basically at the end, all I want to say is that acetyl-CoA activates the enzyme pyruvate carboxylase because it suggests that there's plenty of material available for energy production, and increased affinity for acetyl-CoA means that the enzyme will be upregulated before it should be. And if the enzyme is upregulated and gluconeogenesis thus starts before it should, what's going to happen? You're going to create a futile cycle because it's likely that glycolysis is still going to be doing its thing. The glycolysis pathway is still going to be running. So that's essentially what this question is about. So I'm going to do some more videos and I'll get